Once you've collected data, the next step is to define waveforms that you will then sort into units. This video will take you through the steps to extract waveforms from raw, wideband data. For those of you new to waveform detection and spike sorting, let's quickly review what we are looking for in a waveform shape. For those ready to get started on your data, you can skip ahead to this time. Here we have a very simple example where we are only considering sodium and potassium. In this example, there is a neuron that is close to our recording electrode. Importantly, notice the electrode is extracellular. On the right-hand side, you will see representations of voltage changes at the electrode that are the result of ion movement during an action potential. When there is no activity, there is a baseline of charge. When the neuron fires, an action potential sodium moves into the cell. Since positive charges are moving into the cell, the extracellular potential would decrease. The potassium rectifying current then moves positive charge to the extracellular space. Together, these currents average into the waveform that is captured during extracellular neuronal recording. As you may imagine, waveform shape will vary based on multiple factors including type of neuron, how close the electrode is to the signal, and how many neurons are contributing to the signal. But this shape should give you a basic idea of what we are looking for when defining waveforms. There are 3 steps to waveform detection in offline sorter. The first is filtering the wideband data to remove the slow-filed potential oscillations. For those of you who collected data on an omniplex system, the filtered wideband data is called the spike continuous source, which is one of the data streams you can visualize in Plex Control. The second step is to set an amplitude threshold. Wherever the filtered wideband data cross this threshold, a waveform will be defined and extracted. The final step is to then detect the waveforms. In offline sorter, first we need to load a data file. In the Channels window, we are going to select a data channel by double-clicking. This brings the data for that channel into the timeline view. Here we are starting with wideband data. The wideband signal contains both waveforms, also called spikes, and field potential data. It is the raw recording data. Zooming in to increase the y-axis range in the timeline view, we can clearly see that the signal oscillates as we scroll across time. Therefore, our first step is to isolate the part of the wideband signal that contains the waveform data by filtering out the low frequency signal, also known as the field potential signal. Under Waveforms on the toolbar, select Filter Continuous Data. In this video, we will only be analyzing the selected channel to save time, but you can perform this function across all channels simultaneously. Under the filter parameters, you can choose which type of filter to use. In this video, we are using a Bessel filter, but a different filter may be better for your data. This is a low-cut filter, and we will set the cutoff frequency to 300 Hz. This means any activity in the wideband data stream that is oscillating below 300 Hz will be removed, because it is a low-cut filter. Clicking Apply, we see the filter is applied to our selected channel in the timeline view. The field potential has been removed, and now the signal has a mean baseline centered around 0. This is the filtered wideband signal, also known as spike continuous data. One of the nice features about the filter menu is that we can change the filter settings and immediately visualize the differences in our data. Feel free to play around with the different filters and cutoff frequencies to find the best one for your data. Here we will stick with a 300 Hz cutoff. The next step is to set the threshold. The threshold is an amplitude limit that will determine what is extracted as a waveform. Where the signal crosses the threshold, a waveform will be extracted. The threshold can be set manually using the slider bar in the timeline view, or can be set automatically. In the Waveforms Detect menu, you can choose the parameter for calculation of the threshold. It can be kept at the current threshold. You can use a constant number, which is important if you want the threshold to remain the same across all channels, or you can set the threshold based on the standard deviation in the data, calculated individually per channel. I like to use standard deviations because it allows me to set the threshold in a relatively unbiased way, and it does not matter in these data if it is different across every channel. But make sure you have a reason for why you choose one threshold setting over another. Click Detect and Offline Sorter will find all the waveforms that cross the set threshold. Here you can see there are clearly some high amplitude artifacts. We will ignore those in this video and use the mouse wheel to scroll it in on the important clusters. In the clusters, each data point represents one waveform and similarly shaped waveforms clustered together. Once waveforms are detected, it is very important to review that the waveforms selected are correct for your dataset. To better visualize the waveforms in the timeline view, check the Center Selected box and zoom in on the timescale. Here we can see several waveform shapes in the spike continuous data that cross the threshold. In the cluster view, Clicking and dragging the cursor lets us explore the waveform shapes in different clusters. Each waveform dot is centered in the timeline view as we pass over it, because we checked the Center Selected box. Using the y-axis amplitude zoom, we can visualize the waveform shapes even better. Look at the shape of the selected waveform highlighted in the timeline view. Notice specifically how the waveform rises during the associated repolarization phase, but the selection box indicates the waveform was truncated before the signal could return to baseline. To change the waveform detection settings, select Options on the left side of the timeline view. These three settings at the top of the menu define the length of the waveform. Default is 800 microseconds. A default is just a number the programmers had to put in as a placeholder. It does not mean this is the best, or even the average length of the waveform. As you see in the data, 800 microseconds is clearly too short. We will leave the pre-threshold period at 200 microseconds. Since a waveform is detected by a threshold crossing, we need to define how much data in front of that threshold crossing is part of the waveform. To lengthen the end of the waveform, choose a longer waveform length. Here we will try 1000 microseconds. In addition to the waveform length, the dead time needs to be changed. The dead time can be a confusing parameter, and more about it can be found in section 4.6.2 in the Offline Sorter V4 manual. In the most basic terms, this setting is telling Offline Sorter that if the threshold is crossed twice in the dead time, the second crossing is not to be defined as a new waveform. In other words, two waveforms cannot overlap each other. In general, the dead time should be the length of the waveform. However, if you expect overlapping waveforms because neurons have a high firing rate in your region of interest, you may need to play with this setting. We changed the settings, and now we need to redetect using the Waveforms Detect menu. Again, we will set the threshold to standard deviation. When Detect is clicked, this warning occurs because there are already sorted waveforms in this file. Redetecting waveforms using different settings will erase previously detected waveforms in that file. Observing the waveform shapes again, we now see that the waveform shape gets much closer to returning to the baseline, but not completely in all of the waveforms. I'm going to increase the waveform length and dead time in Options again, and redetect in Waveforms Detect menu. Where I make sure to select the correct threshold. Again, the warning will pop up because I am redefining waveforms. Now we can clearly see the full waveform shape when it returns to baseline. The final waveform shapes you detect will heavily depend upon your region of interest, animal species, potentially the experiment conditions, and many other factors. Therefore, examining the waveforms in your data to decide on the best waveform settings is essential. If you have any further questions about detecting waveforms, you can contact us at support@plexon.com. Thank you.